All right, good. Good morning, everybody. And today, Vijay is going to explain to us about factorization, rounding, duality, and more.
Yeah, great. Thanks, Avi. Yeah, so this is based on some joint work with Oyungli and Asaf Nawar. I plan for most of the talk to be just expository and hopefully say some new things that come from recent joint work. Okay. Yeah. Before I begin stating what factorization theory is, just bear with me. We need about 5 minutes of preliminaries on normed spaces, etc. Okay. So all norms in this talk are over Rn, and sometimes norms are over the space of matrices Rn cross n. Okay. And just as a reminder, a norm is an absolutely homogeneous convex function satisfying triangle inequality. That is, norm of A times a vector x is always equal to absolute value of A times the norm of x. Okay. And I'll refer to a norm space by capital X. By this I mean that it's Rn endowed with the norms of x. Okay. And we'll denote the unit ball of this norm, Bx, as the set of unit vectors according to this norm. Okay, so it's x such that norm of x is at most 1. Okay. Note that Bx is an origin symmetric convex body. By origin symmetric, I mean Bx is equal to negative Bx. Okay. And there is this well-known correspondence between origin symmetric convex bodies and norms. So every norm corresponds to an origin symmetric convex body and vice versa. The way to go from a norm to a body is this unit ball, is by taking the unit ball. The way to go in the reverse direction, so given a origin symmetric convex body B, you define what's known as the Minkowski functional of B. So given B, we define the norm of a point X as the minimum scaling of B. The minimum scaling of X such that lambda times X belongs to B. I messed up. Yeah, it's the minimum scaling of B such that it contains the vector X. So I need X over lambda belongs to B. Okay, those are the basics. Okay, for a set B, I define B polar as the set of points C belongs to Rn such that C inner product X is at most 1 for all X in B. Okay. The dual norm of X. Okay, it's also a norm on Rn.
The inner product is the standard one.
Yeah, standard inner product in Rn. Yeah.
Independent of the norm.
Yeah. Yeah. So the dual norm of a vector C is defined as the maximum of X in the unit ball of X of C inner product little x. Okay. It can be easily checked that the unit ball of X star is just the polar of the unit ball of X. Okay. Now the bipolar theorem says that if you take the polar of the polar, you get B. You get back B. This is true for origin symmetric bodies, origin symmetric convex bodies. Okay, this is a simple consequence of Hahn-Banach theorem. Okay, and in particular, this implies that if we take the dual of a norm twice, we get back the original norm. Okay, good. Now,
You want to say what the the
Yeah.
balls of the L1 norm, the balls of the L2 norm, and so on, what
Right,
they look
yeah.
like, or what? Yeah, just
Yeah,
I mean,
perhaps
I'm
it's
sure
good.
everybody knows. Just to
Yeah. So just a reminder, the LP norm of a vector X. Sometimes I'll actually just skip the L and just denote it by P. Is defined as summation absolute value of the coordinates of X, whole to the P, whole to the 1 over P. Okay, and yeah, I mean, in 2 dimensions, the L2 unit ball, is the perfect sphere, and the L infinity unit ball is the -1, 1 hypercube. Okay, and L1 is this shape. Okay. Yeah. Okay. Yeah. So now we're going to define a norm on matrices, the operator norm. Okay.
don't deteriorate to making your font size smaller and smaller.
Sorry. Yeah, I'll try my best to write big. Okay. Yeah. So so the operator norm is a norm on matrices. So given a matrix A, which we can also think of as a linear map from a norm space X to a norm space Y, we assume X and Y are on Rn. Okay. The operator norm of A is defined as the maximum amount it stretches a unit vector in the source norm. Okay, where you measure the stretch in the destination norm. So said algebraically and denoted by the following notation, the X to Y operator norm. It's defined as the maximum amount that A stretches an X unit vector measured in the Y norm. Okay, and this is of course also equal to maximum AX Y norm divided by X, capital X norm, just by homogeneity. Okay. Right now, just by the dual norm definition on the previous page, we can also write this as maximum X belongs to BX, Y belongs to BY star of Y inner product AX. Okay. And for this reason, I'm going to refer to this also as bilinear maximization from time to time, because you're maximizing a bilinear form over convex sets. Okay. And yeah, I mean, I guess I'll, yeah, if necessary, I will denote it by E comma F of A. So this is defined as max, X is in unit ball of E, Y is in unit ball of F, inner product of X and AY. Okay. So yeah, one slightly confusing thing is that A X to Y norm is actually equal to by Y comma X star. Sorry. By Y star comma X of A.
why did you in the definition of this by, why did you multiply y by a and not x by a?
Yeah, I guess
that's what you want to do. I'm not going to change your notation. You just
yeah, it actually got flipped here. So I mean, it's kind of, I mean, in some situations it's more natural to say yeah, I mean, I agree it's annoying, but in some situations it's just more natural to have it this way.
Okay.
Okay. Yeah. Right. Yeah. So I'm also going to define a related problem called quadratic maximization, which was actually one of the motivations of our paper. Where, we wanted to approximate the bilinear maximum and the quadratic maximum. We wanted to give approximation algorithms for these problems. Okay, so I'll denote this by
bilinear maximization is not convex, even though it's on convex sets, on a product of convex sets.
It is convex in A. In fact, it's a norm on A.
Oh, sorry, it's a norm on A, of course. So it's convex in A. Okay, good. Yeah.
In fact, yeah, thanks. That reminds me.
But so the input to this problem is A, if you want to maximize.
Yeah.
Okay. Yeah.
Sorry, I'm confused about something here. So is the max y ax and then the by one, they're supposed to be just going the other way. One's going from whatever, the one space to the other and then back again. But why is one of them starred and the other one's not?
Right. This is, I mean, so do you mean here?
Yeah. Yeah.
Yeah. This is because the definition of the dual norm. So we can write. No, let's use a different letter.
I mean, the one below it, the by one, how come that's not starred? Why isn't X in the dual norm?
Yeah, okay. I think it's an issue with how I label the vectors. So let's just use different letters. So yeah. Yeah, and how this equality came about was the fact that if I have a vector z and I look at the y norm, I can rewrite that as max of y in the y star unit ball of z inner product y. Does that make sense? Okay. Good. So it's not hard to check that that this bilinear maximization is a norm on A. Okay, on matrices, and since it's a norm, we can actually take the dual, and it will be convenient to look at the dual right now, and it actually arises very naturally. Okay, so note that we have a here it's more convenient to work with the bilinear one. So by E comma F of A is equal to max E belongs to ball E, F belongs to ball F, E inner product AF, right? This inner product can just be written as a matrix inner product. So the Frobenius inner product of two matrices entry-wise. So A inner product E F transposed. Okay. I didn't do anything there. And now we can actually take a convex hull of the set that we're maximizing over because it's a linear function, right? So this is just equal to maximum of the hull. So EF transpose belongs to the hull. M belongs to the hull of EF transpose such that E belongs to ball E, F belongs to ball F of M inner product A. Okay. So I just use the fact that if I maximize a linear function over a set S, then it's equal to the maximum over the hull of the set S, the convex hull. Okay. However, note that this this set, the hull of EF transpose such that E is in ball E and F is in ball F, this is an origin symmetric convex body. Okay. And so now we're just staring at the definition of the dual norm. So like this must be equal to the polar. So if I look at the unit ball of this bilinear maximization norm, right? This set must be the polar of that unit ball. Okay. And naturally one can define a norm corresponding to this, the Minkowski functional, and that is given by the following. So it's denoted, it's called the projective tensor norm, which will be denoted as E projective tensor F, which is the infimum over summation EI Fi transpose is equal to M. It's the infimum over all decompositions, all finitary decompositions of summation EI E norm times Fi F norm. Okay, this may look a little technical at first, but just I insist that people always just think of this set, this hull of unit vector outer products whenever they think of this projective tensor norm. Okay. Yeah. So now that we've defined bilinear maximization and its dual, I also want to define quadratic maximization.
So you didn't define bilinear maximization yet, or the norm, just computing the norm is the definition of bilinear maximization.
Yeah.
Okay, so computing the norm, so given two norms, I don't know, E and F.
Yeah.
These are, sorry, not given, these are fixed. We fix some norms E and F, and now we are given a matrix, and we are asked to compute
to find the norm.
This bilinear. So I don't know, computing the maximum eigenvalue of a matrix is such a problem.
Yeah.
The usual norm, it's the norm from L2 to L2. Okay.
Yeah, good point. And in fact, I'll mention this after defining quadratic maximization to compare the two. But yeah. Right. So a closely related variant to bilinear maximization. This time it's not a norm, and that causes lots of issues. And I'll denote it by Q max of a norm X of a matrix A. So A again, A is a symmetric matrix in Rn cross n. Let's say it doesn't matter, but let's always assume it's symmetric for the purpose of today's talk. Okay. Is defined as the maximum of X in the unit ball of capital X of X inner product AX. Okay. Now this is not a norm, but actually it's a more general problem than bilinear maximization in the following sense. So if I take A as the following block matrix, half times 0, 0, B star B, okay, and I take the ball of X, I define the norm X by its unit ball, which I define as the Cartesian product of BE and BF. Okay. Then I actually just get that Q max X of A is equal to the bilinear maximum E comma F of B. Okay. So quadratic maximization is more general in this sense.
So this was the question. Why aren't you asking? Why is it on the chat?
Oh, because it's not really that relevant to.
Actually, I want to know the answer.
Oh yeah. So Visu's question, were you asking this while I was talking about the projective tensor norm?
Yes.
Yes. So in the special case, when X is equal to L2, then L2 projective tensor L2 is exactly the nuclear norm that Visu mentioned, which is the summation of the singular values of a matrix. Okay, does that clarify the question? Is that okay?
Yeah, thanks.
So actually, it will be even clearer if you tell us why, because that will explain the definition of the tensor.
Yeah. Okay. Well, I mean, so I actually told you why, except in more general language. So the unit ball of the nuclear norm. So the unit ball of the set of matrices whose sum of singular values is at most one. The set of matrices whose sum of singular values is at most one is the convex hull of XX transpose, where X is a vector in the unit sphere.
Okay.
Okay. Yeah. Because of the spectral
Yes.
theory.
So you really write. So you write A or whatever M as a sum of rank 1 matrices in such a way that you minimize the sum of norms of this whatever generates this rank 1 matrix.
Yeah. Okay. Right. So quadratic maximization. Yeah. I just defined that. Yeah. So let me just give this L2 example. So the quadratic maximum over L2 of a matrix A is equal to the maximum eigenvalue of the matrix A. On the other hand, the bilinear maximum L2, L2 of a matrix A is equal to the maximum singular value of A, which, if A is symmetric, is equal to the maximum magnitude eigenvalue, max over I of lambda I of A. So there's a subtle difference between the two. Okay. Yeah. So one final definition, and then I'll describe what a factorization theorem is. Okay. Yeah. So finally, we come to what are known as factorization norms. Okay. Now let's say we have a linear map, A mapping X to Y, and moreover, A is equal to B times C, where C is a linear map from X to L to N, and B, actually, let's be more general here, sorry. Yeah, C is a linear map from X to E, and B is a linear map from E to Y. Okay. Then the following natural inequality holds, which is that the operator norm of A, X to Y, is at most the operator norm of B, of C times the operator norm of B. So X to E, E to Y. Okay, so said in words, the maximum amount that A can stretch a unit vector, an X unit vector, in the Y norm is at most the maximum amount C can stretch an X unit vector measured in the E norm times the maximum amount B can stretch an E unit vector measured in the Y norm. Okay, I said it in words, but that is the proof. Okay, I hope that's clear. Please stop me if it isn't. Okay, so one has this trivial upper bound. Okay, whenever A has such a factorization. Now, so the factorization norm is actually defined as the best possible such upper bound we can have. Okay, so what's denoted as gamma 2 of A is defined as when factoring through L2. Okay, so it's the infimum of BC is equal to A. So infimum over all factorizations of B L2N to Y norm times C X to L2N. I just want to caution people in the know who work in complexity theory. Gamma 2 in the complexity theory world is defined differently. It's defined as some variant of this norm. It's not equal to this norm. I'm using older notation in this talk. Okay. Right. So this is the factorization norm. So factorization theorem is a statement of the form. The best possible upper bound one can have on the operator norm of A is actually close to the operator norm of A. Okay. So trivially, by the fact I mentioned earlier, we always have Ax to y is less than or equal to gamma 2 of A. Okay. But factorization theorems are theorems that that say that gamma 2 of A is in turn at most some constant C depending on x and y times times the operator norm of A. Okay. Yeah, and
so this constant will not depend on the dimension, or can depend on the dimension?
Ideally, it won't. Yeah, I mean it can, but we are interested in situations where the dependence is either mild or it's independent of the dimension.
Okay, so yeah, when we say L2 or LP, we really should think about what dimensions they are. When you say an operator norm X, it counts with the dimension, right?
Yeah, yeah. Thanks for clarifying that. Yeah, it is important to think. Yeah.
Okay.
Yeah. Yeah. Some of these things are best stated in the infinite dimensional setting, but yeah, I mean, given that the applications are finite dimensional, it would be confusing to go back and forth. Yeah. Okay. So yeah. So now Grothendieck's factorization theorem, right? So Grothendieck studied the case of L infinity, like x is equal to y star is equal to L infinity. That is, he was studying this like bilinear L infinity comma L infinity case, which by the fact I told you earlier is also equal to the infinity to 1 operator norm. Okay. And he proved the following more general statement. Actually, the following stronger statement. So he showed that that for any matrix A, the infinity to 1 norm is at most the infimum of D1 B D2 equals A of D2 infinity to 2 norm, A 2 to 2 norm, D1 2 to 1 norm is at most some absolute constant times A infinity to 1 norm, okay, where D1 and D2 are not just any matrices, they're diagonal matrices even. So this is what makes it stronger. Okay. Just a remark, if you remember, I said gamma 2 of A is equal to infimum over BC equals A of the operator norm of B times the operator norm of C. But this is also equal to the infimum over BEC equals A of yeah, the sorry, not E, I'm reusing a letter. Sorry, B GC equals A of C x to 2 norm, G 2 to 2 norm, B 2 to y norm. Sorry, I ran out of space on the right, but you get my drift. Yeah. So I mean, this second equality is really trivial. I mean, one direction can be proved by taking G is equal to the identity matrix. So one side of the inequality can be proved by taking G as the identity matrix, and the other side of the inequality can be proved by taking the substitution. Let's say C is equal to GC. and B is equal to B. Okay. I just stated this in this triple factorization manner to help you compare it to Grothendieck's factorization theorem. Okay, so Grothendieck is saying not only do such B and C always exist, they can also be taken to be diagonal matrices. Okay, he was actually only interested in gamma 2 of A.
Wait, they are not diagonal in that case. I mean, in gamma of A, the substitutions you made does not make them diagonal.
Oh, yes. Yeah, you're right. I just wanted to write it in a way to show you why Grothendieck's theorem is stronger.
Yeah, I mean, all you're saying is that yeah, it's stronger because you can just combine the first two terms, and then you have something from infinity to 2.
Yeah, I guess
it's really, I mean, if you take I guess, I don't know, D1 times A, sorry, what is going on? There should be a B in the Grothendieck inequality in the middle, right?
Yeah, sorry, yeah.
So if you take in your notation, I guess B to B actually D2 times B.
Yeah, that's correct. Yeah.
Then we get you know, the normal definition of gamma 2A.
Yeah, I agree. Yeah.
And so it seems from Grothendieck's inequality that you can always take one of the two of them to be diagonal, no? Either B or C, no?
Yeah. I mean, in particular, that conclusion is fine. Yeah, that's correct. Yeah, but also this triple factorization claim is true, where D1 and D2 are diagonal.
Yeah, I see. But the consequence is if you want to compute gamma 2 of A, we can take C to be diagonal.
Yeah, that's correct.
Up to if you don't mind losing a constant.
Yeah. Okay, good. Yeah, and yeah. So let me first mention some motivation very briefly for talking about this. Yeah, so Grothendieck's factorization theorem has actually, I mean, like, not only did it sort of transform like function analysis, it actually has by now appeared in many different like unrelated places in theoretical computer science. Yeah, one such example is discrepancy theory. Another example is complexity. I have a long to-do list, so forgive me for not fleshing out any of these. I'll refer you to the survey by Lee and Schreibman, where it really is ubiquitous in complexity. Maybe to say one line about it, one of the reasons Grothendieck's factorization norm comes up in complexity, especially in the context of extension complexity, is the non-negative rank of a matrix is closely related to the projective tensor norm I defined earlier, in that the projective tensor norm is an analytic proxy for the non-negative rank. Okay. Yeah, complexity theory, and then Trop had this really nice application to column subset selection. That is, you're given a matrix A and you want to show that it has a large, well-conditioned subset of columns, or you want to find it. And Trop used Grothendieck factorization to give an algorithm for this. Okay.
Is there a relation to matrix scaling?
Maybe. I mean, yeah, I was also.
Sorry, to relation to what?
Matrix scaling.
Yeah, I mean, I was also wondering this, but I mean, I haven't gotten. Yeah, I mean, I haven't gone very far the thought. But as you're saying, implicit in Grothendieck's factorization theorem is the following statement, which is that take any matrix A the maximum of its bilinear form over the hypercube can be approximated by the maximum singular value of a rescale matrix A tilde, where A tilde is a diagonal rescaling of A with some normalization. Yeah, I mean, I won't say too much more about it because I haven't thought about it and don't have anything interesting to add beyond that. But yeah, it does sound like some kind of matrix scaling claim, but I don't think it's related to the original matrix scaling necessarily.
But here you may need negative entries in the diagonal matrices.
You don't. It turns out
yeah, one can consider matrix scaling also in the L2 norm, and then you don't mind. Yeah, it's not clear. But here you're considering just maximizing bilinear forms over the Boolean cube because you're taking L infinity norm.
Yeah, but it does turn out that the diagonal matrices are non-negative in this case.
Okay.
Yeah. Okay. Yeah. So okay. So the purpose of today.
There is also in the application in approximation algorithms of Asaf and.
Right. Yeah. Thanks. Yeah. So the actual reason I'm talking about this. Yeah. So sorry. Yeah. So final application is using this theory and recent work. We give approximation algorithms, and by this theory, I mean more general factorization theory, not just Grothendieck's factorization theorem. We give approximation algorithms for quadratic maximization / bilinear maximization. In more general contexts. Okay.
But if you just look at bilinear maximization, this is but Noga and Asaf did is their papers on both. But if you look at just the bilinear question for L infinity, this is just a cut norm computing the cut norm of a matrix, right?
Yes.
Yeah. So this maximization of L infinity norm over the hypercube for a given matrix A is just basically like finding the submatrix in which the discrepancy is largest.
Yeah, that's correct.
Sum of the values is largest.
Yeah.
And that obviously fits to, I don't know, communication complexity and okay.
Yeah. Right. So the purpose of today's talk, I think, is I want to give everyone an idea for how to prove such factorization theorems, and perhaps give an almost complete sketch of all the ideas involved. Okay, and along the way, we'll streamline some steps in the proofs of these theorems. Okay. So how are such theorems typically proved? So Grothendieck proved his factorization theorem in 2 steps. He first gave a maximization, a dual characterization of the factorization norm as a maximization problem. Okay, so he showed that this quantity infimum of B1 BD2 equals A of B1 norm of B D2 norm. I'm dropping the subscript for brevity. This is actually equal to what optimization people will recognize as a natural semi-definite programming relaxation. Okay, so it's equal to the maximum of unit vectors UI I belongs to N VI. Yeah, So you have a sequence of n unit vectors ui's and vi's, and we look at summation over I comma j.
Vijay, I just wonder even before you do it, I mean, don't you want to, I mean, if we just look at the definition of the bilinear form maximization problem,
Yeah.
I mean, maybe it's nice to just write it down as the maximum of the sum AI, Aij, Xij, or Xiyj, sorry, right? I mean,
Yeah.
then,
I was
then
going to write
this
it
will
under.
make sense. This this relaxation will make sense.
Yeah.
I mean, that's a very explicit form, right? This norm over the hypercube. So it's
Yeah, definitely. I was about to write it underneath. Yeah. So UI inner product Vj, which as Avi was saying, should be compared to the bilinear maximization, which recall was the following. So we maximize xi absolute value at most 1, yi absolute value at most 1. There are sequences of scalars, summation I comma j, ai j, xi yj. Recall this is equal to the bilinear maximum L infinity of A. Okay. Yeah. So Avi was asking me to write this down to compare it to the quantity I wrote above. Okay. So it turns out this factorization norm is actually equal to a maximization problem. Okay. Where the maximum happens over what appears to be a vector relaxation of the original optimization problem. Okay, so xi's are replaced by vectors ui's, and yj's are replaced by vectors vj's. And the condition that xi is at most 1 in absolute value is replaced by the condition that ui has L2 norm at most 1. Okay. Yeah. Another remark, by a simple perturbation argument, we can always assume equality in these things. Okay. The argument would be assume you have some optimal configuration. By just scaling up or scaling down, you can improve the value. So we can always assume that the norms are equal to 1.
It's just convexity, right? I mean, there's nothing.
Yeah. In fact, linearity in this.
Linearity. It's easier to see in the scalar case, and it's the same, right? I mean, the
exactly.
one-dimensional case, it's easy to see, and in the multi-dimensional case, you just look at the one-dimensional case because you have the directions already. So
exactly. Yeah. Okay. So the first step is this dual characterization of the factorization norm. Okay. And Grothendieck originally proved this within factor 2. So Grothendieck proved that above equality, this equality within factor 2. Peach proved it exactly with no loss. Okay. And actually both arguments are some kind of abstract Han-Banach arguments that actually happen on subsets of R to the n. Okay. It was observed much later by Trop and independently Nesterov that equality is a special case of semi-definite programming duality. It falls out directly from semi-definite programming duality. Okay. So that's the first step. And the second step.
Wait. So, Vijay, can you go up a bit for the definition of in the Grothendieck statement? So you say that somehow this is semi-definite programming duality if one looks well enough into it. I mean,
Yeah. I mean, I am going to prove a more general version of this later in the talk. But I want, it's not easy to see directly. I mean, semi-definite programming duality requires work to prove. But it is, these are exactly semi-definite programming duals after appropriate massaging.
I see. Okay, so you will show us. And yeah, it wasn't definitely not obvious to me.
Yeah. I mean, there are several sort of minor transformations to be made, but nothing difficult.
Okay. And so given one, all we want to compare is, the one-dimensional case to the arbitrary dimensional case to show that there's only a constant factor gap.
Exactly, and that's the second step. Yeah, so as Avi said, the second step is to use this maximum characterization to show what's known as Grothendieck's inequality. Okay, that is, this is maximum of summation aij xi yj is at most this maximum summation aij ui inner product vj, which is at most maximum summation aij xi yj times a constant. Okay. I intend to show you a full proof of this, hopefully today, where I'll show you Grothendieck's original argument with constant k is equal to hyperbolic sine of pi over 2. Okay. Good. And in this argument, and as is typical for like convex programming relaxations, implicit is a rounding algorithm. What do I mean by that for anyone who hasn't seen this? Let's say you're maximizing a function over some complicated set S. So we're maximizing f of x such that x belongs to a complicated set S. A common strategy in optimization is to relax this region to a more well-behaved set S prime and maximize f over S prime. Okay, and the hope is that this is a good approximation to the maximum of f over S. Okay, and one way in which one can prove this is by exhibiting a rounding map. Okay, that is for any optimal solution x star in S prime, the rounding map R of x star will satisfy.
So R is a map from S prime to S.
Yeah, R is a map from S prime to S. Yeah, so the rounding function will satisfy f of R of x star is at least, f of x star divided by, say, some constant c. And actually, often it's the case that R will be randomized, as in we map a point in S prime to a distribution over points in S. Okay. If such an inequality is true, obviously the following inequality is true. That is, the max of f over S is at most the max of f over S prime is at most the max of f over S times C. Okay. Right. Good. Now, actually, what I want to do today is talk about 4 different factorization theorems simultaneously with varying levels of coverage, all of which can be proved in this framework of 1 rounding step and 1 duality step. Okay. So let me state the 4 theorems here. So there is Grothendieck's theorem, which says that infimum d1 b d2 equals a, d1 b norm d2 norm approximates a infinity to 1, which is the same as the bilinear maximum infinity comma infinity of a. Okay, so Grothendieck's theorem is for the special case of the norms being L infinity, right? And PCA actually proved this beautiful factorization theorem in a much more general context. Okay. So PCA showed that infimum of BC equals a B norm times C norm. So that is, if you don't care for this diagonal factorization, we have this statement in a much more general context. Okay, it's approximately a x to y norm. Okay, for some constant C of x comma y depending only on cotype 2 constant of x star and the cotype 2 constant of y. Okay, I'm not going to define these things today because there won't be time. But the key point to mention is that this generalizes the L infinity case. So L infinity has constant dual cotype, and this is a great generalization of that fact.
So, okay, so in this case, the map, so B goes from 2 to y and C goes from x to 2. So that's still over L2, right? We are the middle guy is the middle
Always
node
L2.
is always L2. Okay, so
Yeah.
when you go through L2, you never lose more than a constant.
Yeah. You lose a constant called the cotype 2 constant of the norm.
Yeah.
For some norms, this is bounded, actually for a very rich family of norms, but for some it isn't.
When it is, it depends on the dimension, you mean?
Yeah, good point. Yeah, I mean, for some norms, the cotype 2 can be dimension independent for some norm families, and for some it isn't. So L infinity is a family where it's dimension independent, in fact.
And for L2, it is 1, no?
Yeah, for L2 it is 1. And yeah, the only time it is 1 is L2.
Mm-hmm.
Yeah, okay. Yeah, so the duality step in PCA's theorem is different from that in Grothendieck's theorem. The duality step was due to Moret, and it's a more general version, or I mean, or let's say incomparable to the Grothendieck duality statement. This time, it's not semi-definite programming duality, but in the joint work with Uyong Lee and Asaf, we give a different proof of this fact using again, just standard duality theory in optimization. In this case, it's called conic Lagrangian duality.
So this conic Lagrangian duality allows you to write this infimum on the left as a maximization problem.
Exactly. Yes.
Which involves some. Well, maybe you'll show us. Okay, so
yeah. I'll probably approach it in the last 1/3 of the talk. It's kind of technical to write down the maximization version right now. I need to define some things. But yes, just as Avi said, there is another maximization characterization of this factorization norm, a different one than what we saw in the Grothendieck setting, and one can show it. Yeah, I mean, one can show it approximates the operator norm using an appropriate rounding algorithm. And PCA's contribution was a very nice rounding algorithm.
So Vijay, I already see that, well, especially if you want to give us the proofs and maybe talk more about the work of Asaf, you can have next week to continue. I can just,
Yeah.
no, seriously, I mean, consider, sorry, first I don't want you to rush. You planned on, I mean, if you want, I mean, that
Sure.
seems like already beginning to seem for me like a really good idea.
Yeah.
I don't want you to rush over this because it's, and the second, well, anyway, you should consider it and you shouldn't rush.
Okay.
Yeah,
Yeah.
actually, I agree. I would want to add too that if you could send us these notes, if you do continue, that would be great. Or in any case.
Yeah. I mean, okay. I mean, it seems maybe there's popular demand for seeing it in detail, I guess.
Two at least.
Okay. In that case, then I may change the plan today and just go slower, I guess.
That's the main thing I was, yeah. I hope that you'll go slower and show us what, yeah. This looks, yeah, both, you know, sort of really interesting and really useful.
Yeah. Okay. Yeah. Cool. Yeah. Great. Okay. So let's go slower. Okay. Yeah. So this is what PCA showed, and yeah, as I mentioned, you know, there is this duality statement originally proved by Moray, but it turns out one can, you know, just use sort of modern optimization, Koenig-Lagrangian duality to give a different argument for this. I don't want to say it's significantly simpler or anything. Both arguments take a page, but I found the second argument perhaps more intuitive for me. And again, you know, Moray's argument, it's a separation argument taking place on R to the n. And in the latter case, it's a separation argument taking place on R cross R to the n cross n. Okay, and inherent in this is algorithmic possibilities. That is, you can find such a factorization. I mean, under some assumptions, under some necessary assumptions. Okay, right. Yeah, and we kind of use this different proof of the duality statement to prove another closely related duality statement, which allows the following quadratic factorization theorem, which we believe has gone unnoticed so far. Okay, so quadratic factorization. Okay, so we actually show the following equivalence. So infimum of B C, yeah, B transpose CB equals A is symmetric. Okay, of B transpose 2 to X star norm times the maximum eigenvalue of C times B extra 2 norm is equivalent, or I mean is within some constant of the quadratic maximum of A. Okay, if you recall, in the L2 case, a maximum singular value gets replaced by maximum eigenvalue. Just recall that you know, maximum singular value is alternatively depicted by 2 to 2 norm of the matrix C. Okay, so the maximum singular, the 2 to 2 norm, which was the maximum singular value, got replaced by the maximum eigenvalue here in order to obtain a factorization theorem for quadratic maximization. Okay.
So the quadratic maximization is basically maximizing the quadratic form of A, right?
Yeah.
when, over this norm x. So if I look, if x for me is the L infinity norm, again, we want it on the hypercube.
Yeah.
Right?
Yeah.
We know that unlike the bilinear case, it cannot be, there's no constant factor approximation.
Yeah.
Seems like it requires logarithmic
factor.
Yes.
Excellent. Thanks. Yes. Sorry, when I may have accidentally said constant. So yeah, the equivalence here is hiding the type 2 constant of the norm x squared. Okay. Again, I sort of don't want to define this today, but the point is that for L infinity, as Avi is saying, this is actually equal to log n. Okay. I want to compare this to the bilinear case. So the quadratic case is more general. Okay, it sort of captures more problems. And as a result of this generality, the factorization theorem actually necessarily must lose this logarithmic factor, even in the L infinity case.
So I still don't understand if the type 2 constant is logarithmic or square root of log.
Yeah.
Didn't you mention that it entered also the inequality in the, but it entered PZS proof. So PZF for L infinity gives something weaker than
he gives a weaker constant, but he gives a constant. So
why is it a constant in the case of L infinity? It seems like for L infinity, if this is a type 2 constant, x star and y will be L infinity, right?
Yeah. So this is actually related to the fact that the co-type 2 constant of the dual of L infinity is constant, but the type 2 constant is square root log n. So it's the difference between type 2 and co-type 2 in this case. So
sorry, the type 2 is constant. Type 2 is constant, the co-type or whatever. One is constant and the other is not.
Exactly.
I didn't even notice that you said something different in both cases.
Yeah.
Okay.
Yeah. Sorry. Yeah. I mean, and just to write down, algebraically what I just said, it's well known that the type 2 constant of x is an upper bound on the co-type 2 constant of x star. And then the other direction, if it's n-dimensional, if the norm is n-dimensional, then you have type 2 is at most co-type 2 of x star times log n.
Or square root or something.
Yeah, I think in this inequality, maybe log is lost and it's lossy, but in the L infinity case, it's a square root log.
Okay, got it. Okay. Thanks.
Yeah. Right. So we proved this factorization theorem for quadratic maximization that we think has gone unnoticed before, and actually so we use this quadratic factorization theorem and PCS factorization theorem to get approximation algorithms for quadratic and bilinear maximization in more general settings than were known before. Yeah. Okay. Of course, necessarily the type 2 and co-type 2, like constants of these norms have to be bounded for us to get good results. And also that's not even necessary. We need some more assumptions, but I'll not get into that today. Yeah.
Okay, you can also take a break if you want some time.
Yeah, thanks for reminding me. It's 11:36. Yeah, let's take a break now before I get into the proofs. Great. Good. All right. Yeah. So those are the three. So there's Grothendieck's factorization. There's a much more general PCA factorization. there's a quadratic version of that general factorization that necessarily has a worse dependence on the constant, but on the other hand, works in more general settings because quadratic maximization is more general than bilinear maximization. And for expository reasons, I cooked up another factorization theorem, which is a quadratic version of Grothendieck's factorization. Okay. So here the statement would be infimum of d b d equals a of d 2 to x. In this case, we're talking about L infinity. Sorry, so 2 to 1 norm. B, sorry, not 2 to 2 norm, but the maximum eigenvalue B, lambda max of B times D infinity to 2 norm. This is going to approximate the quadratic maximum according to L infinity of A within log n. Okay. The characterization of this dual norm as a maximization problem is sort of, I mean, probably has just not been mentioned in the literature. I'm just doing this as a, for expository reasons. However, the second part, the rounding part, is well known. Is a well known rounding algorithm. Okay, and I think it sort of provides a gentle introduction. It's the easiest rounding algorithm I can give an exposition of. Okay.
In this quadratic case, also the D can be diagonal.
Yes, thanks. Yeah, D is diagonal. Yeah. I wanted this one to stress the connection to Grothendieck, and also to stress how remarkable Grothendieck's inequality is, because it gets a constant with the caveat that you're doing it for bilinear maximization.
Mm-hmm.
Okay, so on Grothendieck's, this is O of 1. Yeah. Okay.
You know, Vijay, it's sort of unrelated, but
yeah.
Given the the other things that Grothendieck is famous for, why did he go to this norm issue? Why, what motivated him to go into this problem?
So yeah, so I think his PhD was actually, so I mean, I was reading his history, and apparently, he started his PhD in some high-powered seminar, and he wasn't able to follow the seminar because he didn't have a classical mathematical background. And he was advised, I forgot by who, to go to Schwartz and study with him, study analysis, because he's not good enough for algebra. And then Grothendieck did his PhD on functional analysis, and he was interested in studying, if you're given a norm X and you take a tensor product with itself, so X tensor X, what kind of norms exist on this space? Okay, and in other words, what are norms on matrices that one can generically define starting with the norm X? And all these objects naturally pop up. And he wanted to just study these norms, and he arrived at all of this by in this study. Yeah.
Okay, so it's before he went back to algebra and made all these revolutions. Okay.
Yeah, and actually, I think on Wikipedia or something like that, it's mentioned that Grothendieck has this list of his 12 favorite contributions. This is the 12th most important. Last on the list.
Probably made the list 12 long so he could include it.
Yeah. I'm glad it wasn't 13th. Yeah. So okay, yeah. So let's. I think the revised plan for today may be that I will prove the rounding. Okay, yeah. Sorry, I'll write this on a new page. Yeah, so there is quadratic version of Grothendieck, then there's Grothendieck, then there is quadratic version of PCA, and then there's PCA. Okay, and then there is the dual characterization step, and then there is the rounding step. Okay, rounding algorithm step, not necessarily an algorithm, I guess. Yeah, and I guess, oops, sorry, I accidentally erased. Yeah. Yeah, so today the revised plan will be to show you this and this. So the quadratic Grothendieck and Grothendieck rounding algorithms in full detail. And initially I plan to also show you the duality step here, which is essentially extremely similar. I mean, at least our proof will just sort of specialize to this, this, and this with appropriate changes. Okay. So I'm not going to show, I didn't plan to show you these, specifically. Sorry. Yeah, those three specifically, because they're sort of extremely similar to this, at least going by our proof. Yeah. However, I won't show you this today. I'll focus on the two rounding algorithms and try and show those carefully. Okay. And finally, I just want to mention, sort of this is like the simplest version of Gaussian rounding. And it turns out that obtains the optimal dependence you can hope for. And it's the same is true here. So the type 2 loss is the best you can actually hope for in this case. And again, the rounding algorithm is the same. It's the simplest Gaussian rounding algorithm that I'll show you. Okay. On the other hand, Grothendieck's rounding algorithm is somewhat non-trivial and nuanced. In a similar vein, PCA's rounding algorithm is quite non-trivial and nuanced. Okay. And actually, yet another interesting feature of PCA's rounding algorithm is it's not instance oblivious. That is, it looks at the matrix A in order to, the rounding map looks at the matrix A, or depends on it. Okay, this is just an interesting side note. And I mean, just looking at his proof, I mean, I'm almost tempted to say that it might be necessary to have such a rounding algorithm for this, but it's not clear. Okay. Yeah, and yeah, so I'm probably not going to show this or this, but I will state the rounding algorithms. I won't show the analysis. I will state the rounding algorithms maybe in the next talk. Okay, so first I'm going to show this, and second I'm going to show this, and that's the plan for today. Yeah. Okay. Right. Yeah. So our goal is to show the following inequality now. Okay. So we have quadratic maximization. Max x1 through xn belong to plus minus 1. Sorry. Summation over ij, aij xi xj less than or equal to max of vectors u1 dot 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 un in the unit sphere. Okay, summation over ij sorry, I need to make them in the unit ball.
It doesn't matter, you say, but right?
Yeah,
but it's more convenient to prove it this way.
Yeah, it doesn't matter in the bilinear case. In the quadratic case, it matters.
Oh, I see. Okay.
Yeah, it's an unfortunate technicality, but it won't really come up.
Okay. Yeah, but we lose linearity, I guess, in the, in the quadratic case.
Exactly. Yeah. Aij ui inner product uj and less than or equal to log n, order log n times the same summation ij aij xi xj.
N initially denotes the size of A, right? A is an n by n matrix.
Yeah. A belongs to R n cross n and is symmetric, let's say, for simplicity.
Yeah. So what I guess should be obvious is that when you relax from scalars to vectors, you never need to go to vectors of dimension above n.
Yeah.
Well, that's obvious, I guess.
Yeah. This is as I was saying, this is another way to rewrite this expression is that it's the inner product of A with a PSD matrix bold X, and any PSD matrix can always have its entries written as the inner product of two vectors of dimension at most n. Okay. And the constraint that the gram vectors have L2 norm at most 1 corresponds to the constraint that this PSD matrix has diagonal entries at most 1. Okay. So another way of writing this program, I mean, as I just stated, is you maximize over PSD matrices X with diagonal entries at most 1, A inner product X. Okay. Right. And the main and only idea here is that the multivariate Gaussian distribution is uniquely given by the first two moments. Okay. So what do I mean by that? I mean that one can always sample a Gaussian vector H in Rn with mean 0 and covariance boldface X. Okay. And I'll specify how you do it. So let G1 through Gn be IID Gaussians. Okay. And then you just take HI to be equal to the inner product of.
Just a second, Vijay. So you are proving, of course, only the second inequality with the factor log n, right? You sort of started the proof of this. The first inequality is trivial, so we are just, relaxing. So you're going to show that if some x is the optimum of the of the relaxed program, then we can find scalars, right? We can find scalars to replace them and lose only a log n in the optimization.
Indeed,
and to find scalars, this will sample vectors according to the Gaussian distribution that X defines.
Yeah.
Because it's given to us, and do something with them.
Exactly. So implicit in what I'm going to say For technical reasons, it's, what I'm saying is a little bit imprecise, but implicit in what I'm going to say is, and what Avi was mentioning, is the following rounding strategy. Sample G from the covariance matrix, sample H, I guess, in my current notation. H from the covariance matrix bold X, return H divided by infinity norm of H. Okay. Recall our goal was to return a vector in the unit ball of the L infinity norm, so in the hypercube, okay, that moreover has good value. Okay, it can be shown that if you do this process polynomially many times, this will have value within 1 over log n. Okay, the reason is the denominator, the L infinity norm of a Gaussian vector with possibly correlated entries, is at most order log n. Okay, I'll show this in detail now. I just wanted to describe to people who haven't seen Gaussians, multivariate Gaussians before, how one samples a Gaussian, with respect to an arbitrary covariance matrix. Okay, right. So let G1 through Gn be IID Gaussians. Okay, we want to sample a Gaussian vector that has mean 0 and covariance X. Okay, since X is PSD, it can always be written as the Gram matrix. So Xij can be written as Ui inner product Uj for some ensemble of vectors. Okay, by the spectral theorem and the fact that it's PSD. Okay, and now we will take the ith entry of H to be this IID vector G inner product with Ui. Okay, and it can be easily checked by looking at expectation Hi Hj. This is equal to expectation of summation Gi Ui, Gj Ui jth entry times summation Gj. Okay, sorry, I abuse notation. Sorry, Gk Ui kth entry, Gk Uj kth entry, right? And it's easily checked. This is exactly equal to Ui inner product Uj by just looking at what terms go to 0 and what terms don't. Okay. Right. Okay. So armed with this fact, let's prove the above inequality. Okay. So again, as Avi mentioned, this first inequality is trivial. Okay. So you just take the vectors Ui to be the elementary vectors scaled by Xi's to show the first inequality. Okay. For the second inequality, we're going to sample Gaussians. Okay. So let bold X be the optimal solution to, let's say, star. Okay, so this is what I mean by star. Okay. Okay. So then we have A inner product X is equal to summation over Ij Aij Ui inner product Uj, which, as we showed earlier, is equal to summation over Ij Aij expectation of Hi Hj. Okay, which of course is equal to the expectation of H inner product AH. Okay. Now by the definition of quadratic maximization, right? Just a reminder, quadratic maximization over L infinity of A can be alternatively defined as maximum of X inner product AX, X is non-zero, divided by X infinity norm squared. Okay, so by exactly that definition, we have the inequality. This is at most quadratic maximum over L infinity of A times expectation L infinity norm of H squared. Okay, which is at most, order log n times quadratic maximum over L infinity of A. Now the reason for this order log n is the following. So we have n Gaussians, H1 through Hn, possibly correlated. It doesn't matter because we're only going to apply union bound. Okay, so each guy has the distribution of a Gaussian, so it has tail e to the negative t square. So the probability of Hn being more than t, or in this case, probability of Hn being greater than log n, or any Hi for that matter, greater than log n, square root log n times an appropriately large constant, is at most 1 over n to the constant. Okay, and so we can take union bound over all the h's, right? And this intuitively speaking tells you why the expectation of the maximum of n Gaussians is at most square root log n, and so this quantity is at most order log n. Okay. Yeah, and just a reminder, the rounding strategy implicit in this argument is that you take the optimal solution bold X, you sample a Gaussian according to that covariance, and then you normalize it. So you want this vector to be in the hypercube. It's not in the hypercube necessarily, so you divide it by its maximum entry, and the maximum entry is going to be square root log n with high probability. Sorry, I made a mistake here. Okay, and because this is a quadratic problem, you lose log n. You lose the square of the normalization. Okay. Okay. Right. So we proved the rounding part of the Grothendieck quadratic case. Okay.
So Vijay, you mentioned that this is tight. It's probably easy to find a matrix, maybe the matrix of the complete graph or something for which it's the log n is the worst.
Yeah, it's I think complete graph works. I don't remember exactly. So Asaf and Noga and I think Makrichev brothers have a paper on this, where the gap, I think, is the logarithm of the size of the independent set or something like that.
No, the chromatic number.
Sorry. Okay, yeah, logarithm of the chromatic number.
Yeah, so if it's a bipartite graph, which is a linear case, then you get a constant.
Yeah.
And in the complete graph, I guess you get log n.
Yeah, I think you're right. Yeah, I would need to double check. But one thing I know for sure is that if you take a Gaussian random matrix, that should also get log n, I believe.
Okay.
Yeah. Okay. Right. So now let's prove Grothendieck's inequality. Okay, which as stated earlier goes as follows. So we have the maximum over xi. X belongs to plus minus 1 to the n. Yeah, y and x. Summation over ij, aij, xi, yj is at most the maximum over vectors summation over ij, aij, ui inner product vj, which is at most some constant k. In this case, we will prove hyperbolic sine of pi over 2 times the bilinear maximum. So infinity comma infinity a. Okay. Which is, I mean, yeah, as shown earlier, it's the same summation in over ij, aij, xi, yj quantity. Okay. So we're going to show this inequality. Now, as was the case earlier, I'm going to show you the analysis, and then later I'll state the rounding algorithm implicit in the analysis. Yeah, again for technical reasons. Actually, sorry. In this case, I think I can state it. Yeah. Okay. With some possible error that I'll correct later. Okay. So the rounding strategy is as follows. Okay. Let Z be the matrix whose ijth entry is given by Zij is equal to ui inner product Vj. Okay. And let Z tilde be the matrix where you apply the trigonometric sine function entry wise to Z. So by the square bracket notation, I mean that you apply the function entry wise to Z. Okay. And pi over 2 times Z in this case. Okay. And finally, we're going to sample independent Gaussians, G1 through Gn. Okay. Independent Gaussians. We're going to set xi is equal to G inner product ui. And then we're going to set yj is equal to G inner product Vj. Okay. And sorry, yeah, I made a slight mistake. Yeah.
What is where are you using the GIs?
In this inner product. So G is the vector of GIs.
Oh, G is a vector of GIs. Sorry, you're okay,
Yeah.
good.
Yeah. Yeah. Yeah, so now I'm going to take xi to be the sign of G inner product ui and yj to be the sign of G inner product Vj. Okay. Yeah, so this second step is somewhat mysterious. But
just a second. Oh, sorry, the GIs are scalars. Okay.
Yeah.
Good.
Okay. Yeah, so this second step is somewhat mysterious, but it'll it's sort of this pre-processing transformation necessitated by the choice here at the bottom. So SGN represents the sine function, so the sine of what you get back. Okay, so another way of stating step oh, sorry, I made another mistake. So this has to be u tilde I v tilde j, where z tilde ij is written as u tilde I inner product v tilde j. Okay, so this is the rounding strategy again implicit in this algorithm. Let's not focus on this too much. I'll show you the analysis, and then that'll make it perfectly clear why this is the rounding strategy implicit in the analysis. Okay. Right. So yeah. So the analysis is as follows. Okay. As earlier, recall that we can rewrite the maximum, right, over the hypercube as the maximum over the convex hull of the vectors xy transpose. Okay, so we can rewrite the bilinear maximum infinity comma infinity of A, just because it's linear function maximization, as the maximum of z in hull of xy transpose such that x comma y are in the hypercube. Okay. Of A inner product Z. Okay. Yeah. Now above, we have this convex relaxation. Let's call it RLX of A. Right. Note that we can rewrite RLX of A as the maximum of A inner product Z, such that Z Z can be written as UI inner product Vj for unit vectors UI Vj. Right. Yeah. So now let's give a name to the set, that is Z, such that Z is equal to UI inner product Vj for UI L2 norm at most 1, Vj L2 norm at most 1. Okay, the set of matrices that can be written in that way. Let's give a name to the set as S2. Okay, and let's call this set S1. So to show the desired inequality, it's yeah.
L1 are basically just monochromatic rectangles, I guess, right? Or well, I guess in the 0, 1 case it would be just I mean, oh, so it's in the convex hull of all of these, yeah.
Yeah.
So yeah, it's a convex hull of all these monochromatic.
Yeah.
So is there a simpler description of them, or just?
Not to my knowledge. Yeah. In the L2 case there is, but L infinity, yeah, not to my knowledge.
Okay.
Yeah. Yeah. So it's possible to show trivially that S1 is a subset of S2. Okay. The non-trivial equivalence will be to show that S2 is inside sine h of pi over 2 times S1. Okay. And yeah, and clearly we're just maximizing a linear function over S1 on the left and maximizing a linear function over S2 on the right. So once we show this equivalence, we are done. Okay. Just recall one thing: S1 is the unit ball. Okay, S1 is the unit ball of the projective tensor norm that I defined at the beginning of the talk. So infinity, just as a you don't need to see the definition of the norm again. All you need to know is that it's a norm. Okay, because we're going to apply triangle inequality. Okay. Okay, so yeah, so let's prove the second inclusion. Yeah, and to do so, we're going to have two steps. Okay. So the first is the Gaussian rounding identity. Which says that the expectation of the sign of G inner product of vector U times the sign of G inner product vector V, where G are again IID Gaussians. It's a vector of IID Gaussians, and U and V are, let's say, arbitrary vectors in the L2 unit ball. Okay. Sorry, in the L2 unit sphere. Okay. Then this expectation depends only on the inner product of U and V, and in particular, it's equal to sine inverse U inner product V divided by pi over 2.
So this is exactly what's used in the rounding algorithm of the max cut of Gormans and Williamson.
Yes, yes. Yeah, so in fact, yeah, I mean, Grothendieck actually used hyperplane rounding first in his proof.
So I guess the easiest way to see it is just whatever dimension U and V are, they just span a plane.
Yeah, yeah. So as Avi said.
Oh, sorry. So you're going to prove it.
Yeah.
Okay.
Yeah. Right. Yeah. So as Avi said, by rotation invariance of Gaussians, okay, we can rotate U and V so that U and V lie in the two-dimensional plane. So we can take U to be equal to E1, and we can take V to be equal to cosine theta, comma sine theta, where theta is the angle between U and V. Okay, we can always rotate any two vectors U and V so that this is the case, right? So theta is equal to yeah, theta is, I mean, I guess cosine inverse of U inner product V. Yeah, so we can always rotate the vectors, and by the fact that the Gaussian distribution is invariant to rotations, yeah, we obtain this. Okay, so I mean, yeah, so we obtain that we can study this question in the two-dimensional plane. Okay, so now, yeah, all we need to do is study the following question. Okay, so we need to calculate. So given two vectors U and V in the plane, if I sample a random hyperplane, when does this hyperplane split the vectors, and when do they lie on the same side of this hyperplane? Okay, when this hyperplane splits the vectors, this will be -1, and when this hyperplane doesn't split the vectors, their product will be +1. So to calculate that expectation, we want to say +1 times the probability of splitting, sorry, of not splitting, and -1 times probability of splitting. Okay, and of course, probability that a randomly chosen line splits two vectors, is a function of just the angle between the two unit vectors, right? And yeah, and just I'm not going to write down the details, but just like a simple calculation yields this identity. Okay. Okay, so we get that identity, and yeah, in particular, this means that if I take a matrix Z whose ijth entry is ui inner product Vj, okay, and I set hi to be a Gaussian vector G inner product ui. Sorry, I set xi to be a Gaussian vector G inner product ui, and I set yj to be the Gaussian vector inner product Vj.
You are not going to change the. You're not going to take the sign of the entries in Z.
Yeah, I'm not going to do that now. I mean, yeah, some of this inversion step becomes
Okay.
yeah, obvious after first showing it on a generic matrix Z. Yeah, I mean, as I was saying, the inversion step is motivated by this identity. Yeah, so yeah, so we have a matrix Z like this, and then we sample Gaussians G, and then we set xi and yj as that. Then this identity in particular implies that.
So xi is really the sign of this. There is a sign missing, right? The xi is the sign.
Sorry, thank you. Yeah, SGN of this, yj is SGN of this. Yeah. Okay. Yeah. So then, using this identity, entry-wise, applying this identity entry-wise, we obtain that the expectation of xy transpose is actually equal to sine inverse applied entry-wise to Z divided by pi over 2. Okay. So in particular, observe that whenever Z belongs to the set S2, that is the set of matrices that can be realized as inner products of unit vectors, then sine inverse Z divided by pi over 2 is the expected. Oh, sorry. Yeah, let's just say it this way. Is a convex combination of hypercube vectors. We obtain this because x and y are hypercube valued random variables, and the expectation of xy transpose is equal to this matrix sine inverse applied entry-wise to Z divided by pi over 2. Okay, because of this, we obtain that whenever Z belongs to S2, then this matrix sine inverse Z divided by pi over 2 is a convex combination of hypercube vectors.
This it's not hypercube vectors, it's hypercube matrices or something.
Yeah, hypercube outer product.
Rank 1 hypercube matrix.
Yeah, exactly. Yeah, exactly. Right, and therefore sine inverse applied entry-wise to Z divided by pi over 2 belongs to S1. Right? Okay, we're not done yet. Okay, so we have this weird identity that whenever Z is in S2, then sine inverse applied to its entries belongs to S1. Okay, so this actually forces us to do some kind of inversion. Okay, this brings us to the second fact. That if I have a matrix Z tilde, okay, consider any matrix Z tilde. Consider any Z tilde, then the projective tensor norm of the trigonometric sign applied to z tilde entry wise is at most the hyperbolic sign of the projective tensor norm of z tilde. Okay. Now I'm going to prove this fact on the next page, but before I do that, observe that if we plug in z tilde as sine inverse applied entry wise to z, then we know by what I showed you previously that the projective tensor norm is at most pi over 2. Because, I mean, because of this fact I mentioned above, that once you divide it by pi over 2, it's in the unit ball of the projective tensor norm. Okay. So it's in the unit ball of the projective tensor norm. Okay, so the projective tensor norm of this guy without the normalization of z tilde equals sine inverse z is at most pi over 2. Okay, so then we obtain that sine inverse of z projective tensor norm is at most hyperbolic sine of pi over 2. But this guy is just equal to z. So we have proved that z is in the ball of the projective tensor norm, which in other words, just to describe it again as I did earlier, is the hull of xy transpose such that x comma y belong to ball of L infinity. That is the hypercube. Okay, which in other words is S1. So if we prove 2, we need to prove 2. If we prove 2, we are done. Okay. Right. So how do we prove 2? This is the combination of two observations. Okay. Yeah. I'm sorry, I'll go 5 minutes over time. Okay. So the first observation is that is that if A comma B belong to S1, that is the hull of outer products. I'm not going to keep writing it. Okay. Then A entry-wise product B also belongs to S1. Okay. The reason is the following. If A is a convex combination of hypercube vectors, and B is a convex combination of I'll use lambda bar, of hypercube vectors, then A entry-wise product B is equal to summation over ij lambda I lambda bar j xi circ xj. So entry-wise product of the vectors yi circ yi circ yj transpose. Okay. And of course, note that if xi and xj were vectors in the hypercube, then xi entry-wise product xj is a vector in the hypercube. The same with y. And therefore, A circ B belongs to S1. That is the convex hull of hypercube order products. Okay. So yeah, I mean, I kind of hit it, but by homogeneity, the fact that I just showed you implies that if I have a matrix Z and it belong, if I have a matrix Z, I have the property that taking the ith power of the entries of Z and then looking at the projective tensor norm just is upper bounded by the ith power of the projective tensor norm, just by applying this previous fact iteratively. Okay. Okay. Good. So we proved that, and now, yeah, the second fact is just triangle inequality, which we know is true because this is a norm. Okay. So combined with these two facts, what we're going to do is we're going to write out the Taylor series of the trigonometric sign of Z tilde and just apply triangle inequality. Okay. So now we're trying to prove 2. Just remember that's what 2 was. Okay. So we have trigonometric sign applied to Z tilde is equal to summation of minus 1 to the I sorry, minus 1 to the I divided by 2I plus 1 factorial. This is the Taylor series of sin x, Z to the I, Z tilde to the I. Okay. Therefore, applying the two facts I mentioned, triangle inequality and the powering fact, we just get that the projective tensor norm of sine of Z tilde, infinity tensor infinity, is at most summation I equals 1 to infinity 1 over 2I plus 1 factorial. Observe that the minus 1 became a 1 because we have absolute values coming in after we use triangle inequality, times projective tensor norm of Z tilde to the I, right? Which the right hand side is just the definition of the hyperbolic sine function. So this is hyperbolic sine of infinity. Okay. Good. Yeah. So that completes the proof. Yeah. Sorry for taking so long, and sorry it's more algebraic and not filled with intuition. But yeah, I mean, implicit in this entire argument I gave you is that the above rounding algorithm I mentioned will work. That is, you take the optimal ensemble of vectors Ui and Vj, you apply this inversion operation, entry-wise inversion operation to it first to get a different matrix. Then you do Gaussian rounding on that different matrix, and then you'll have good value.
Is there any reason that, well, okay, first, thanks. Thank you. So, yeah, let me ask my question. Let others ask questions. You use the sign. I mean, why not use other functions? So is it people, I'm sure, try to, is there intuition? I mean, there's some magic happens, which allows you to avoid what happens in the Gaussian rounding. In the Gaussian rounding, you have to take a union bound over all
Gaussians,
all entries, and you have to take the maximum. Here, you seem to not worry about this because all the values are bounded simultaneously.
Yeah, that's a good question. So let's recall, in the quadratic case, we sort of had this dumb strategy where we sample this Gaussian vector G, right? And our hands are tied. Somehow Gaussians have enough fluctuation that some entry will be square root log n. Okay. And at the end of the day, we wanted to produce a vector inside the hypercube. So we went with the dumb strategy of just normalizing this G so that it's inside the hypercube, right? But that need not be the only way you produce a vector inside the hypercube, right? Recall, like we want two things. Okay, we want to produce a vector V inside this hypercube such that V inner product A V, let's say, or U inner product A V if we're in the bilinear case, is sorry, let's not use U and V. My bad. Sorry. Yeah, we want to produce X and Y in the hypercube such that X inner product AY is large, right? And yeah, and they're in the hypercube, right? Now the previous strategy corresponds to just like dumb normalization to put it inside the hypercube, whereas the new strategy can be thought of as the following. So you you sample this Gaussian vector just like earlier, okay, and in order to produce a vector in the hypercube, you find the vector in the hypercube that maximizes the inner product with G. So set X is equal to argmax of X in the unit ball of the hypercube of X inner product G. Okay, and your intuition is that if A inner product GG transpose is large, which we know by the by design, then A inner product XX transpose should also be large. That's the intuition behind this, and of course the bilinear version of this statement. Right. So now what happens when you set X to be the vector that has the maximum inner product? So the vector in the hypercube that has the maximum inner product with G. Well, by duality, like it can be checked. It can be checked that the best X to take are the signs of the Gaussians Gi. Yeah, and yeah, this strategy is more generic. Sort of one can define the strategy for more general norms, and actually it's no longer entry-wise. This fact that the maximizer in the unit ball is the entry-wise sign of the Gaussians. This is no longer true in general norms, but the general strategy still applies. And in fact, Pissier's algorithm has a step that looks like this. Yeah. So yeah.
More questions to Vijay.
Well, I just have a question. Is there a paper yet or a draft?
Yeah. So yeah, we recently submitted something to stock. I can send you the paper.
Oh, okay. Yeah, that'd be great.
Yeah, we don't discuss Grothendieck's inequality much at all, but yeah, I mean it's more about this general factorization theory stuff.
Yeah. That's fine. Yeah.
More questions? Okay, thanks. That's great. So whoever wants to meet will meet at 1:15.
Great.
Okay. See you. Thank you very much, Vijay.
Yeah, thanks everyone. And